recording. Yeah, okay, started. Okay, cool. So basically the vortex lattice method is basically, do you remember, say for example, the panel method?
Yeah.
The panel method that we did in like earlier in error. The way the panel method, I'll just start from there. That's what. So the panel method, it has like kind of like a bunch of panels kind of, and like imagine there's like panel and all that.
Are you sharing something, by the way? Because
I forgot to share screen. Right. Yes, my bad. Sorry. Okay, yeah. So imagine there's a bunch of panels, and each of those panels are like making swirlies. Like it's just a line of vortices, kind of. Yeah. And I know this is like stuff that you probably already know, but you can imagine like all those panels are making like swirls, and though each of those is like a constant strength of swirls, kind of. Or was it a source? Mm-hmm. It's a source vortex panel, right? My bad. So there's a vorticity for all of them, but there's also like a source. A source is basically like, yeah, I'm sure you know how the sources work, but yeah, it's just like pointing outwards basically.
Yes.
And like each of these are pointing out. So if you were in a recording, so you like skip past this. So each of those are like pointing outwards, and you don't know like each of these sources. So like you don't know each of the source values. It's like 1 and then source 2, source 3, source 4. And like there's all these other sources, and you don't know the value, the strength of each of those sources. What you also don't know is you don't know the vorticity. The vorticity is basically gamma, and you don't know what gamma is. This gamma is just assumed to be a constant. But either way, what you have is you have like n number of sources, and you have 1 gamma over there, and you don't know what any of these values are. But what you can impose is you can impose conditions so that you have enough equations that you solve all of these values. That's basically like how the source panel method works, right? This is source panel.
Yeah.
Source. So basically you're just developing enough equations so you can like actually like work it out. This is basically the same idea, sort of, except that it works in 3D. So the idea basically is like, imagine I'm just going to have like a sheet. So imagine like a sheet of something. And you could either use a horseshoe or you can use ring elements, doesn't matter. But you can imagine just different shapes basically. And so what you're imagining here is you can imagine like squares, kind of like a rings. Like, yeah, even like when you look at like an aircraft skin, you can kind of actually see like like squares like this, but like kind of like of rivets, but kind of like that. But like the idea is like you're just imagining like little squares kind of like little like rings basically. And they're meant to like overlap on each other, but like I didn't draw it like that. It's meant to be like, it's kind of like a window sort of thing. I don't know. So it's kind of like that, and like it comes down across and up like that. Okay, I'm just having a lot of fun drawing. No, okay. Each of these red windows is its own like source. It's a source ring, like a ring source, not source. It's a vortex sort of. So the idea is you're imagining each of these rings. I'll take one of those rings, and you can imagine this. It kind of like imagine it like as a model to like kind of suck air through it, and it pushes down into the middle. So imagine like air pushing down through the center. So through the center, and like imagine it kind of like pushing down sort of. Okay. And you can imagine just kind of like a net instead of like a full sheet. You can imagine like a net that does this, which is what you're really imagining. What you're really imagining is just a net like this, and each of these is like doing this. It's basically just sucking air through in it, or something like that. Okay, and each of these is doing this effect. Okay, the thing that makes this useful is because some of these cancel out. So you see this over here, it cancels. It should cancel a bit. Yeah.
Yeah, understand. Yeah.
So it's that sort of thing. But like the thing is, what makes this useful is because even though this is like a hypothetical model, it's really good because it can be used to approximate the lift and the airflow around one of these aerofoils or one of these wings and stuff.
Okay.
So yeah, that's the like conceptual idea with this sort of thing. Just basically just imagine each of these just like kind of sucking air through it. But the thing is, the net effect of this, the overall effect is, if you see this black sheet, there is no air going through this black sheet. That's basically what you're saying. So the condition that you impose, like here, up here we impose conditions. The condition you impose is that there's no air going through this and through any of these panels. That's basically the condition that's imposed here. Likewise, the condition that you impose is basically that there's no air through the panel, through the sheet. So I'll write that in black. That's basically the idea that you're implementing. So first, what you need to do is you need to be able to construct the sheet. If you don't have anything, you first need to create a sheet. First, what you imagine is basically like you're doing a series of transformations. That's what the tutorial was going through. Basically, what you start off with is I'm going to just imagine like a perfectly flat horizontal wing, and then it's just like in its own grid lines. Yeah, imagine it like in grid lines or something like that, and like just across just grid lines as usual, as you'd expect. And you can have different amounts of spacing for that, and the spacing is like assigned in the tube. In the tube they just went through. So there's like linear spacing, cosine spacing, sine spacing. There's all sorts of weird stuff here. The way that they assign the directions is also pretty important, because it's not normal to like how we normally think about. Maybe, I don't know, might or might not be what we normally used to. So basically, yeah, x-axis is basically this way, or like vertical axis is x and horizontal axis is y, which is really weird to think about. But yeah, took me a while to think about this. And z-axis is in and out of the page. So z is in and out of the page. Yeah. The easiest way I'd say is the z-axis is out of the page. That way it's easy to think about. If you have like a positive z, it's just like coming out of you into your face. Easy to think about. Anyway, okay. So first thing that they asked us to do was I think they asked us to put camber. I think they put the order in as well. So the way that you're actually coding this business, by the way, normally you do this as a mesh. And what the mesh does is basically you have XX, or actually you would have YYXX. The reason is because Y is a horizontal and X is the vertical. So you have to do YYXX. And then is equal to mesh grid. And then you have an array of Y values and an array of X values. So that's just Y, X sort of thing. It's like you have like a mesh grid of like whatever, like your X and Y coordinates are. That's basically what the tutor just said. They put that somewhere here. It's like, yeah, here, X lin, Y lin is equal to mesh grid X, Y, X. They did it that way is because, again, I said Y is horizontal, X is vertical. So they have to swap that. Anyway, the way that each of these matrices look like is also really important. The way that the Y looks like is basically YY looks like kind of, or you don't even need to call it YY. I'll just call it Y and X, doesn't matter anyway. So Y kind of looks like, it's just all the Y coordinates. So you can imagine each of these points have coordinates at each point, like here. And so this is just the Y coordinate of each. So if you have an X and Y, this is 0, 0. This is 0, 1. This is 0, 2, and so on. And then this would be like, say, 1, 0, and something like that. So what you imagine is you take every second number, and that itself is the Y matrix. The mesh, basically. The mesh of Y is just every second number here. So you can imagine 1, 0, this is 1, 1. And this would be like 6, 1. And so every, sorry, my bad. Y is, this is Y. This is X, my bad. Because this is Y, this is X. This is really weird to think about. You know what, I can just rename the numbers. That's probably easy to think about. Sorry. Let me rename the numbers so it's easy to think about. Sorry about that. Horizontal, I'll put X, so that's 1, 0. 1 across, 0 down or up. And so that's, yeah, so then that's, what's this? This is going to be 2, 0, 3, 0, and something like that, right? And so you can imagine these are your y coordinates because y increases across like this. This is your x coordinates. And it's kind of weird because x and y is sort of flipped here. But don't worry about that. But anyway, at the end of the day, what we have here is we have 6 across and then 1 down, like that. So what you're imagining here is that the y matrix, the entire matrix is going to be, basically it's going to go, the y
Wouldn't
coordinate
that be 7, 1?
Sorry?
Wouldn't that be 7, 1?
No, 6.
Oh, okay.
Yeah, 1, and then this comes 1, and then this is 2, 3, and then all the way until 6. And then this also just comes back down to 2. This is down with 3, and then, you know, as usual, this comes down to 6. So this is your y matrix, how it's going to look like. The same, in a similar fashion, x, instead of changing like this, it changes the other way. So then this would be like 0, ... At some point you will hit 0.5, and then at some point you hit 1, because 1's down there. And then basically it's not going to change across. So that's going to be 0, 0, 0, and all the way until 0. And then this is also going to be 0.5, 0.5, all the way until the end, which is 0.5. And then this is just going to be all the way until 1. That's how the x and y coordinates look like, because that way it gets every combination of x and y. This is 0, 0, which corresponds to this first point.
Yeah.
That's how this works, yeah. And then like eventually you can get every point on the mesh like this. So this is the x. Yeah. Initially it starts off like this. Then what you need to do is you start off, say, you can imagine the z, because it's completely flat, the z is all 0. So you can just imagine these are all just zeros. So you just imagine it's the zeros. Okay. Whichever you need. Yeah, they're all 0. It doesn't really matter. That's what you start off with initially.
Okay.
After that, what you have is you first have to incorporate camber. And the only thing that camber really affects is just your z. If you think about it, if a sheet is cambered or not, all it does is it makes it taller or not. Like all it's really going to do is, if you have a wing that's flat or a flat panel, it just makes it curved. So it's only like, this is the x direction and this is the z direction. So all it's really doing is just changing like the z values.
Yeah.
Yeah.
Cross section is changed.
Yeah. You're going to have to like assume a camber distribution or use a specific aerofoil. We don't, as of yet, we don't know which aerofoil we're meant to use, I think. But the thing is, this is meant to be your mean camber line. Yeah, mean camber line. So, yeah.
They haven't like released that thing, right? Like
they haven't revealed
MATLAB grader.
They haven't told us what it is. For me, I just assumed this was like a sine sort of wave. So imagine it's like some number, sine, and then just x times pi or something. Who cares? It doesn't matter.
Yeah,
I just assume something so it looks like a curve. You know, so I can imagine like a 0.1 times, just as an assumption, just guessing here.
Okay.
Yeah, like just as a placeholder, I'll put it. So that way, at least it looks curved. Maybe that just might help. Makes sense. But it doesn't even matter. You can even go with a flat one. No one cares. You can add that in later. Once they actually tell you what it is, then you can account for that.
Okay.
Yeah. So don't worry about that for now. Okay. That was the first thing. The second thing that I've said was in the sheet. I forgot yeah. So you did camber and then you need to do taper. So taper, basically what you're doing is you're imagining in, if you look at from the top view, what you're imagining is you first start off with like a rectangular flat sheet. And so what you're doing is this axis from up here is your y axis, and this is your x-axis, right?
Yeah.
Yeah, we just talked about that earlier. That was your y-axis and that was your x-axis. Forgot where it went there. Y-axis and x-axis. So what you're imagining now with this is basically that for it to be tapered, you can either taper it about the leading edge or about any other particular y coordinate or any particular x coordinate, right? You can taper about the 0.25 chord. That's quarter chord. You could taper about the center. Depends wherever you want to taper about. That's just a choice that you're going to make. For me, I'm just going to tell you about how to do it for the quarter chord, but it doesn't really like matter at all. Yeah. The idea basically is that you want to kind of shift the axis from x to x plus 1/4, and then from there you work it through, if that makes sense.
Okay. Yes.
So the idea is basically like, how was it again? Wait 1 sec, let me pause share. And can you still see my screen?
Yes, I can.
Is it moving?
Yeah, I can.
No.
Like, is it moving or is it like stopped, like paused?
It's stuck.
Okay, good, because I'm opening my code and don't want to let anyone see that. That's kind of sketchy. 1 sec, sorry.
That's okay.
But so far everything here made sense, right? Maybe it's stuff that you already know, maybe not, I don't know.
Yes.
Yes, no, I don't know. Yeah, sorry if I was boring you.
No, it was not. Like, no. When someone like, if some student explains, you'll have more like clarity, because you will try to explain in the most simplified version and like with a lot of details, if that makes sense.
Yeah. I get you. Oh wait, my bad. We don't need to worry. Oh, do we? Yeah, we did. Never mind. How did we do this? This was okay. I got it now. Okay, that made sense. Now I realize how I did it. Okay. You can still see my screen now, and like it's
yes.
Okay, cool.
Yes.
So what we did is basically you take every coordinate and you subtract it from this line. So say for example, this was an x coordinate of 0. This is like x equals 0.
You're pointing something? I don't think we can. Okay, yeah, now, yeah.
This is like x. This line over here is x equals 0. This is like x equals x equals 0.25 times a chord, whatever. Yeah. But the idea is that what you're doing is you by subtracting every coordinate from this line or from this x value, you only worry about the x values, by the way. You don't worry about the y or z. The y value, the wing doesn't get any longer or shorter, and it doesn't move up or down when you taper. You're only affecting the x values. You make it like taller or shorter, like, you change the chord-wise direction. Yeah. Anyway, so what you're imagining is you subtract, so you take x coordinate, or take x coordinate, and then you minus your 0.25c times a chord. And so this shifts the axis. So this is now the new axis. This is this business. This makes this like the central bit.
Can you change color? Because that, I mean, it's not really visible because you're just using black, I guess.
Oh, fair enough. What I was saying is that this line is, if I want to make that my center,
it will become the new axis, right? Now,
yeah, it's a new axis when I subtract 0.25. And this is like the new axis. Yeah. And so you're making everything relative to this. Then what you do is you multiply by you multiply this by your taper ratio. And then what you do is after you apply your taper ratio, then you add it back. And so what you're doing is you're applying your taper ratio about this axis, and then you shift it back to the original axis. If that makes sense. So then my new x-axis is back to where it was before.
Okay, got it.
If that makes sense. I just wanted to make sure if I did this correctly. If I explained this wrong, then that's kind of bad. Yeah, okay, no, I've explained this correctly, I think. Pretty sure this is correct. Okay. Anyway, okay, so back into the thingy. Basically, forget that. Basically we have apply taper. After we apply taper, we apply twist. So basically what you're imagining here is yeah, so now with twist, what you're imagining is with each section, so you imagine still it's a rectangle, but like it's kind of like now a trapezium sort of thing. You can imagine now it's tapered. What you're imagining is you have each vertical section here is still parallel. Throughout the entire time we do any of our transformations, these vertical lines stay parallel. This is still your x-axis. This is still your y-axis across this one. Yeah. All these x-axis lines will always be parallel, no matter what your transformations that we're doing throughout the entire time. Anyway, so these planes would be parallel. Like, yeah. So to twist it, what you're doing here is this one will be untwisted, right? Because you can't twist the root chord.
Yes.
So what you're applying here is actually you're applying a rotation matrix. Rotation matrix basically just comes as cos, sine, negative sine, cos, and then you have like some angle basically. Doing something like this, I think I got the matrix right. The negative might be in a different direction. I forgot which way it goes. I think it's that. I think it's this, but anyway, I might have gotten this wrong. It doesn't matter. The rotation matrix basically rotates by an angle theta. So what you're imagining is here, say for example, if there's like 1, 2, 3, 4, 5. There's 5 of these here, and imagine if this is rotated. About like whichever axis that you choose. There's this particular axis that you need to choose as well. That's whatever you decide. I think normally they pick that the 0.25 is like the quarter chord, is the is the new axis that we work with. But anyway, so it's rotated about this quarter chord. And imagine if I rotate this by 45 degrees, for example. So what you're actually imagining here is that because there's 5 panels here, so there's like 1, 2, 3, 4, 5. This 5th one must have rotated 45 degrees. So this first one must have rotated 9 degrees. This one would have been 18 degrees. Imagine this as now 27 degrees, and this is 36 degrees. Did that make sense?
Yes.
Yeah, because like it has to rotate equal amounts across to make the final rotation.
Makes sense. Yeah.
Yeah. So what you're actually going through is you're going through each y coordinate. So you loop through each y coordinate like this. And then for each of these, you have a certain x and z coordinates for each of these. For each of those x and z coordinates, you rotate it by the corresponding amount theta, which is linearly spaced, because these theta has to be like linearly spaced from there. If that makes sense.
Yes.
Yeah.
Yes.
Yeah. Okay. Hopefully that explained it. And when you're rotating about this axis, if you just directly multiply it, then it'll rotate about the leading edge, because that's where the x-axis goes from. I forgot where it actually goes from. I think it might go from, one sec, sorry. I need to actually get where it comes from. Sorry, my memory's not that great. Let's see, taper, not taper there. Where am I looking at? Twist, that's right. To rotate it about, what did I do? Oh, okay. I think I got that. Did I do this right? I think I did this right. Okay, wait, I think I got this right. So tapered value, then you get the location, which is that's just the tapered value. Then you need to take the, okay, got you, I think. Okay, all right, I think I got what I did there. Sorry, I need to understand my own code, because like that's basically understanding Jack's code. What I was saying basically was that like what you're effectively doing is you take this as your like y-axis. What you're doing is you're going to shift it so that you get these points, and then from there you add quarter chord. So for each of these panels, so you can imagine like for one of these panels, I'm going to take like one section sort of. Okay, this is the y, and this is the like kind of zooming in. So imagine if I zoomed in here. This is the zoomed in. Yeah. And so what you're effectively doing is basically for each vertical panel, it's like down like this. And so what you're actually doing is you're taking this distance. This distance is basically based off what you did in the taper earlier. And so this is already the new x value. This is the x value that you got from before. This is the new x value.
Yeah.
Or like this is now the new x or something like that. I don't know. Okay, so this is your new x value. And then from there, you have to add a quarter of the chord. And so what you have is basically the first x value. So this is x1. And this is the end value. And so basically you're just taking a quarter of the difference. The difference xn minus x1 is the entire chord. And so if you want to take quarter chord, then it's just 1/4 of that value.
Okay.
And so you find where the quarter chord is. So basically what you're doing is you're finding where the quarter chord is, and then you shift your axis to each of those points. So for wherever you're doing it, you take like your x value minus the quarter chord. Again, because now you shift your axis back to this. Depending on whichever piece you are, is just subtract a quarter chord, and the chord is calculated for each of these iterations. If that
makes sense.
Yeah.
Yes.
So now once you know what these are, then you can apply your rotation matrix, because when you apply your rotation matrix, it rotates that particular. So you can imagine like, that's my amazing aerofoil. You do not see my amazing aerofoil. Okay, this is an even better aerofoil. And then when you rotate it, instead of rotating about here, what you're doing is you're shifting the axis back to here. And then when you rotate your axis back to there, then you rotate about this point instead.
Okay.
Rotate about this. And so by rotating about that point, then now you can imagine the aerofoil looks like this. My drawing skills are not the best, but something like that, if that makes sense.
Yes.
Yeah, so that sort of thing. So you're rotating about the quarter chord instead. Again, that number can be changed, so your x-axis is shifted by different amounts. But that's basically what Jack's code is doing.
So here we are basically we're just shifting the axis from one to another, right?
Basically.
Okay, got it.
And then after that, you can add your original, or you can add it back so that it's the original axis. So you can like apply the rotation and then add it back.
Okay, got it.
You can imagine as well as the rotation changes the x values. And so it only tells you the delta for all of those x values or something. And so what you can do is you can just add them to the previous values or something like that. The z values are new, completely brand new. They've changed, but the x value is kind of like a delta sort of thing. So you can change it like it's only like a little change in x sort of. Maybe, I don't know. Maybe I'm interpreting this wrong, but yeah, something like that. But you basically take a look at what Jack did, because it makes a lot more sense. So basically, it's like. So what he basically did, so it was here it was up this top. So this is basically, shift is 0.25. So this is quarter, and this is your chord. So this literally just says x shift is basically the amount that you shifted, your axis, which is a quarter chord. And that's what you calculate.
And then you're adding back the shift.
Yeah, right? So yeah, exactly. Your initial position plus the quarter chord. So so this is x location 1 plus quarter chord. That's basically what that line says. I should just work on Jack's code. Gosh. Okay. And then you apply the rotation matrix because it's about that point. And then you just basically extract the new x and z coordinates from the rotation when you multiply the rotation and all that. Once you're done with that, then basically add it to the previous value, the original value, like the first. Because the thing is, this is now the x sweep 1i basically just says you add it from the leading edge, basically. So your x coordinates get added according to the leading edge, if that made sense.
Can you repeat that? Like, or it's some other word?
So this last bit reconstructs the mesh grid from values. Now you got your rotated values, but you don't know. It's like what you've done is kind of like you've unpacked this and you've taken one section, then you've rotated it, but then you need to place it back where it belongs. Because
Yes,
when you
got it,
rotate
got
it,
it.
you kind of misposition where it belongs. So you have to put it back where it belongs. That's what it's saying.
Okay.
And so this last part is basically putting it back where it belongs. Sorry, this X twist here. So it says this is where this X sweep business is where it belongs, and the ZT it's not changed because like originally has not been twisted. The Z values would be like it's already like the Z values is the rotated values. There's no shift that you need to account for. This X-way business is accounting for the shift that you did earlier.
Okay.
Yeah, that's sort of
I
like
think
a
this
loose
code really helps like to get a better
and get a better
understanding.
understanding. Yeah. But yeah, that's basically how that works. And then after that, you have sweep. Sweep is a relatively easy one to think about, I think. Basically, when you're thinking about sweep, you're basically just adding everything like. So you imagine, I'll put it this way. So if you have, yeah, I'll just write. What you're imagining is like this. And so what you're doing here is take your y-axis, but like along x down. And so what you're doing is for each of these at certain regular intervals, you just basically add plus basically an extra amount plus tan sweep angle or y tan sweep angle. And then you basically just add that to every x value.
To every x coordinate.
Every x coordinate. And then you just do that for every like loop sort of.
Oh yeah, get it.
Or
So
you could just add the two
like
matrices directly, but like, yeah. Or something like that. Yeah. If that made sense.
Yes. Does. Got it.
That makes sense, right? Yeah.
Yeah.
Okay. Yeah, so that's basically how that works. It just hops across basically. And that's why they did the tan leading edge times gamma, but you can use like a different angle if you wanted to, but I just went along with what they did because thinking about shifting more axes is just confusing.
Makes sense. Yeah,
but you can
yeah.
imagine shifting another axis as well if you want to, but like if we don't have to worry about it yet, then don't worry about it.
Okay.
Yeah. Okay, so that's basically how sweep works. And then after that, there's a final thing, which was dihedral. Dihedral is the easiest of them all, actually. The dihedral is basically instead of adding on the y, you instead of adding along the x-axis, just like how we did it here in sweep, the dihedral does the same thing, but it does it for the z-axis.
Okay.
So imagine if you have yourself like a flat plane. So this is now, okay, so imagine this is like, imagine like a flat sheet and you're looking at it from the thin edge side. Okay, this along here is the y and up the top is the z. So you can imagine even being curved or whatever, it doesn't even matter. It's basically you have z upwards and you have y across, just like how you have y across here, but you're looking from the sides. So you can imagine like your eye looking like this, looking this way. So you'd see it like completely like flat or something like that. Either it's flat or curved, it doesn't matter what it is. What you're doing is at every increment or whatever regular increment that you have it like according to your spacing or whatever over here, you have all your spacing and all that. So for each increment, what you're doing is you have like, you're imagining it to be angled like this. And so this is your angle, which is gamma. And so basically it's just like a y tan because it's like the amount that you have to shift it by, if that makes sense. So if you have a particular y value, basically you just have this gamma. Gamma is equal to this height over y. And so y tan gamma is equal to this height that you're shifting it by. If that makes sense.
Yeah.
So h, and so you imagine this is a y distance. So it's like circuitor, if the algebra makes sense. So for each of these values, you're just adding, it's like z is equal to z plus y tan gamma. Like it's as straightforward as that. You're just shifting it by that much.
Yes.
And you do that for every coordinate. So that's just basically how you build your week. Other than that, it's not.
You just have to make matrices for each of it and like do it.
Yeah. But the thing is, you can treat each of the x, y, z coordinates separately. And most of the coordinates that you have to deal with, most of them, don't care, like it only affects one coordinate at a time. Say, for example, if you're talking about camber is only to do with the Z coordinate. Taper is to do only with the X coordinate, for example. It loops over every Y coordinate, sure, but it's only changing the X coordinates. Twist affects both X and Z, so maybe that's a bit of a complicated one, but they gave you code for that. Sweep is only affecting the X coordinates, and then dihedral only affects Z coordinates. So the entire time, it's like only one coordinate at a time. So that's why the mesh makes it easier. But yeah.
Oh.
Yeah.
I think for the difficult part, they've given the code.
Yeah, sort of. Yeah. So that's how that works. And then after that, then you're building the panels. So what you're imagining is these ring panels that I was saying earlier. So what we did now is we have like what they call geometric panels, basically. So you have like these actual like, imagine like, how do I explain this? Okay, so I'm going to take this green, where'd it go? This green diagram. Imagine this green diagram, but I'll redraw it like so it's scaled differently or something like that. So imagine my actual thing looks like, I'll just make it like a 3x4 or something. Maybe it's just easy to think about. These are your physical geometric panels. These are the panels that we literally just drew as each of our coordinates that we got from earlier. These are all the coordinates that we had from earlier before.
Okay.
I'm just drawing it flat because it's easy to think about. Yeah. From here, what you're doing is you imagine at every so what you imagine is every quarter chord. So what you're doing is you're taking each of these panels. So let me give it a distance. I'll call this the chord length, or the chord length of each panel. Imagine each is a flat sheet, and what you're doing is you're taking the quarter chord across each panel here. Quarter chord over here, and a quarter chord here. And what you're really doing is you're just making a new mesh, which is your mesh of vortices. This is a vortex mesh. Okay, so this vortex mesh is a hypothetical model. It's like a math model. It's not real, like as in obviously this can't exist. This is like your idealization or whatever. Yes.
Yeah, got it.
Okay, got that. Okay, so basically now from here, each of these, so you see these, you imagine the ring that goes around here. That goes into here. And each of these will be that mesh that does that.
Okay.
If that makes sense. Yeah.
Yes.
Okay. Now, the thing that you don't know though is what you're imagining is each of these holes will have a certain vorticity to it. Okay, it's going to have a certain gamma value. This is gamma. So each of these will have like the gamma 1, gamma 2, gamma 3, gamma 4, and so on. And you'll have like basically gammas for all of them. Okay, actually you should actually call them like, technically you should actually call this 1, 1, and then 1, 2 or something, and a 1, 3 or 1, 4, something like that. But like, who cares?
Yeah.
You just basically, effectively, you just have just a bunch of like vorticities, and each of these like cells has an unknown vorticity. So what you're actually solving, your vortex lattice method, what it's really doing is it's just figuring out, like with a simultaneous equation, puts a condition, and with that condition, you can solve each of these. And so the condition that you're doing, the other thing as well, is that now when you shift all of these as well, at the very end here, what you're imagining is as well is that there's a wake over here, and this wake makes one really big, it makes a really big last one. And this is just accounting for the entire wake so that you can apply the Kutta condition or Kutta condition, whatever they call it. Yeah. So there's a last set over here as well. Yeah. Anyway.
Understood.
Yeah. So with all of these, the condition that you basically are saying is that there is no, so with the sheet, I can imagine the sheet like this. The flow going through any of these sheets, so flow, 0. Because if it's a solid sheet, it can't go through. And so that's the condition that you're putting. And so what you're imagining is, yeah, sure, each of these rings is kind of like sucking air through it, but it's like the net effect from all the other sheets should make it like so that there's no air going through it. And so what
Understood.
you're really doing is you're taking a normal at a particular point at every control point. And that control point is like a 3/4 chord or something like that. But it's, so because you've shifted here, you've shifted each by 1/4 chord. And what you're doing is you're making this particular one at 3/4 chord. What you're actually making is about halfway from, like this is about halfway.
Okay.
From each of these, if that makes sense.
Yeah.
Yeah.
Yes.
But regardless, what you can do is you can construct all of these dots, like all of these control points. And so what you're saying is the flow normal to those at these control points need to be 0.
Okay.
So basically what it's saying is that there's no flow going through the wing. Yeah.
Yes.
You can't say there's no
Like
flow
the
throughout the
initial-
entire section, because like that's kind of hard to do. Like you need like volume integrals or something like that. But it's easy just to do it for each of these points.
Okay.
Yeah. If that makes sense. Yeah.
Yes.
Okay. So that's basically like the overall condition that you're doing is like just the dot product needs to be equal to 0. And so what you're doing is each of these points will create a separate equation. And so what you have is each of these panels will have one unknown, but each of these panels will also have a dot, and that dot will create one more equation. And so you have exactly the same number of dots as you have unknowns. And so you have enough equations to solve.
Okay.
Yeah. So what you're doing next is the assignment notification. Do I have the notification open? I don't have it open. Okay. Let me just check what the notification says. Is this it? Yeah. Yeah, that's it. Okay.
The way you name your files, practically done.
To be honest, I love naming my file almost done when I am almost done. It really helps me finish. Gosh. Anyway, okay, so the geometric panels is the black panels that I did here.
Okay.
The black panel that I drew is the geometric panel. And then basically what it's saying is, discretize wing, yep, as input, and returns vortex panels as an output. And so what it's doing is basically apply and then make your shift, and then you have to account for the last bit as well. That's what part B is asking. And then in your report, and then also return a normal vector on each panel and include the additional vortex. Lecture 8B actually goes through, I think if I can close this. This is week 9. Okay, week 8. 8B basically goes through explicitly what are all these formulas that you meant to use, which explains this pretty well. These are exactly the same thing that we did for the horseshoe. If you check through the lecture, I think it has it. So it was somewhere here. It was here. Okay, so this is your normal vector that you use. And so what you're doing is you just imagine each of these panels, because of this x1, x2, x3, x4 business, is you're imagining each of, I'm taking the black panel. So imagine the black panel here. This is x1, the vector. The vector is because it's written as x, y, z, x1, y1, z1. Imagine it like that. And so that's x1, this is x2, this is x3, and this is x4. It's convenient to put those vectors in a form as well. It's also really convenient when you label all of these and you write this all out as a cell array. That's what they were talking about in the lecture. Basically, the thing that makes it convenient is with each of these black panels, you make them as one entry in the cell array. And then with each of those, you can store all 12 coordinates because there's 3 on each corner. So you can do that for each 4. Like you can set it as a 4x3. So it's like, you can imagine in each cell, there's a 4x3. So this is going to be x1, y1, z1, and then x2, y2, z2, x3, y3, z3, and then x4, y3, z4. Sort of like that. Imagine this, and this is one cell.
Yeah.
And so you can imagine,
you have to make it
like, you have to make a cell matrix basically for each panel. So this is panel 1, panel 2, And so like you do it for each of these,
So
and then you can like
each of
make an entire
it will have
matrix.
its own matrix, right?
Yeah, it's like a matrix of matrices.
Yes, makes sense.
Okay, so you can imagine building that, and you can make a quick code that actually just builds this for you. The thing that makes this convenient is because you can use the lecture notes exactly the same formulas. You can just type them up and you can get all those values. And each of these can be stored in its own cell matrices or whichever way you want to store it.
Okay.
If that made sense. Yeah?
Yes, yes.
Yeah, okay. So now once you have all of these values, this is your center of pressure. Your center of pressure is your little point over here. You have the normal and the point at which the normal acts accord. That's your control point. So all the blue points that I did, all these blue points that I worked out earlier, that is your control point. And that's the point where you're making the normal, like the normal flow needs to be equal to 0 there, which is this normal vector. I think you're also meant to normalize this normal vector. So like make it a unit length for everywhere, because you're going to need that for your calculation later on. Later on, when you work them out, you basically just sub it into these formulas. Say, for example, if they're asking for the induced velocity at an arbitrary location, basically you have the formula they gave you in the lecture, induced velocity calculation, n is equal to r1 cross r2, r1, r2. And so you basically have that vector, and then you can just basically just apply it everywhere you need it to.
Okay.
And so
I
think that's overall the idea with that. Yeah, so far my code, I've gotten up to this stage.
Okay.
So that's basically wrapping up part B. I haven't made it into a function yet, but I just got in the code to work. Putting it into a function is not hard. But
okay.
Yeah, so that, and then so I'm basically up to here where I can just apply those induced velocity on the arbitrary location due to a rectilinear vortex ring composed of 4 finite vortex segments. In your report, describe how your function looks and provide some verification that it produces the correct outputs. Yeah, so something like that. And so you just apply the formula they say, basically. So just what is the induced velocity? You just pass it through and you just chuck it the values that you need to. Yeah.
So as is like due in 1 week, and they've not released that MATLAB grader because
apparently it was released today
like,
or something.
Really?
Maybe I need to check that later. Anyway, that's not important. What happens here is basically that these are the normal flows times this business. This kind of like, imagine a factor out and then it's equal to this. The idea is that the total normal flow, so this is like kind of into the wing and this is out of the wing, and so the total amount into and out of the wing needs to be 0 so that there's no flow through the wing, if that makes sense.
Okay. Yes.
Yeah, so that's the idea through that. Yeah, so there's that. So it's just simply boundary conditions and construct the influence coefficient matrix. So basically all we are doing is first we need to create all our U values, the Uij business, I think. That's part C, sort of something like that. And maybe your Ni business. And then part D is creating the matrix. Part E is about solving the matrix and then calculating lift and drag. And then part F is discussion.
Got it.
So it's not too hard. Yeah. So basically,
it's not too hard, but it's kind of lengthy. That's the only thing.
So instead of UAB, UBC, and UCB, instead of that, what you're doing is you're using instead of like the 3 of them, because you have 4 edges, because it's just like
got it.
You have to just do the 4 of them. It's not too hard. Yeah, you can throw that in its own like function, because you can apply that function to each of those panels.
Yeah.
Oh, good.
Yes.
Yeah.
Hopefully I didn't take too long. Sorry for my extended
No,
rant.
it did not.
It's very helpful.
It made it very clear, in fact. Yeah.
Oh, thank you.